All right, this is a continued tutorial on how to model and map flood risk from sea level rise. So we're on part 4. We've downloaded and processed our data, and lastly we adjusted the heights of floods under the different scenarios, taking into account the fact that we're dealing with meters, and also that we have different datums, or different datum that we're dealing with the digital elevation model, which is the heart of how we're modeling this. So what we're going to focus on is modeling the reach of these minor, moderate, major floods, essentially, and the way that we're defining those floods is by their probability of occurring. So they have the same level of probability as the current minor, moderate, major, but the reach of the flood, how far inland it goes, is going to be different because the water will be higher. So we're going to use these numbers as our flood areas. So I'm going to be identifying in the flood, in the DEM, all the areas that are below that elevation, essentially. So in this first we'll start with a minor flood, which is 2.86. So if we look back at our DEM for Boston, we're going to be identifying areas that are low enough so the water will penetrate further inland. And I'm going to so what I'm going to do for that is I'm going to use a tool, another analysis tool, and this one's going to be the spatial analyst tool called raster calculator. So let me close this guy there and go back to the tools. And okay, so I want the raster calculator, which sounds more we want to make sure you're grabbing the spatial analyst tool one too. So you'll see this one. The first one is image analyst. We want the spatial analyst. I don't think it actually really matters, but just in case. We'll take that one. So what we're doing is we're going to basically do a simple matrix math, which don't get hung up on that. It just means that we're going to look at which numbers fall below a certain level. So in this case, keep in mind that this raster, this layer that we're looking at, is basically a grid of cells, and every single cell has a value in it that corresponds to the elevation of that point, wherever it is. So what we want to do is do a very simple mathematical operation that says just identify the cells that are below the level of the flood level, right? So that, because if they're below that elevation, then they're prone to get flooded. So again, the number we're going to start off with is 2.86 meters. So we're looking for areas that are below 2.86 meters in height. So the way we do that is in the raster calculator dialog box, I'll double click on my raster, and then I will look for the less than operator. So I'll click on, there it is right there. And then I just type in 2.86. And then what it's going to do is it's going to output a new raster that gives me the result of that. So I'm going to name these carefully so I don't get confused, because it would be very easily to generate a lot of junk and then get lost. So I'm going to call it DEM and 2_86. Again, don't put any spaces in your names for rasters. Make sure it's going into the geodatabase where all your other stuff is, or however you're saving it. It's all going to the same location. So so it's DEM 2_86. So that's the height. So I'll click run. Okay. So the areas that are in red now, so it generated a new raster that consists of zeros and ones. And essentially what it means is the ones are areas that met the criteria. These are below 2.86 meters. So presumably these are the areas that will flood. So that's what we're after. We're going to process this further though, because you may notice that you can see along the coast, right along the beach in front of Moakley Park is red, not surprisingly, but you might see some interior areas that aren't necessarily clear how they would get flooded from the coastline, and we're going to fix that. All right, so what we want to do first is we're going to isolate just the areas that are floodable. So we have this new raster called DEM286, which just consists of ones and zeros. We don't care about the zeros, so we're going to get rid of those. And we're going to do that by using a tool called reclassify. So I'm going to go back into my tools here and type in reclassify, and I want the one that comes from the spatial analyst tool, so not the one from the 3D analyst. So spatial analyst tool. So I'll click on that one, and the input raster will be this DEM286. And so what we're looking at is this table down here. So this is the values it has right now. So what we want to do is we want to turn all the zeros into no data. So I'm going to double click there under new and type no data just the way it looks over here. And then over here is going to be the ones that meet our criterion. So you could make it a 1, or you could put in the value. I could put 2.86. It's going to be integers though, so it'll round it up, but it doesn't matter. I mean, as long as we know what it is. So all we're trying to do is just keep one type of cell that has an actual value. That's going to generate an output, also a new raster. So again, I'm going to keep a consistent naming scheme. So I'm going to call this one DEM2_86 RC. So this is just me keeping track of what it is I've got here. So that way I can know what it is I'm looking at, and I can backtrack and know, because we're going to generate a lot of these things, so you want to make sure you know what they are once you've generated them. So I'll run that. And so what you're going to end up with then is a new raster that only consists of the one. So let me turn off all the other stuff that's going on here. So now the green areas are the areas that would potentially flood just based on their elevation. So and you can see Milkley Park, just kind of looking in closely, shows it. Although notice again how it's not connected to the water line, right? So how would the water get in there? So in that case, we say that it's not hydrologically connected. So that means that it's not likely to flood that way. So we want to clean that up. So we're going to turn this raster into a polygon layer, a vector layer, and that will allow us then to do that kind of manipulation. So I'm going to, now I'm looking for another tool. It's called raster to polygon. So I'm going to type that in here. Raster to, poly, there it goes. Conversion tools, raster to polygon. There we go. Okay. So the input raster, it will be the one that we've just reclassed, DEM286RC. The field value is fine. That's what we're taking. It's going to also put out a polygon feature. So I would again be cautious. Name everything very deliberately so you know what you got here. So I'm going to, for this one, I'm going to say less than LT2_86. So this is just my very simplified naming scheme to just keep track of. It doesn't matter what it is as long as you know what it means. And everything else can stay the same. So I'll run that. Okay, and then what I end up now is a new polygon layer, the pink one, that is going to be, it's identical to the green. The difference is that this is a vector layer. It's basically lines and interiors versus a raster layer, which is cells or a grid. Okay, so this, once we have a vector layer, this allows us to actually do some cleaning up about the places that may not be realistically floodable given the circumstances. So I need one other thing here. So what I'm gonna do is I want to identify, or I want to keep only the polygons, the pink areas that actually touch the coastline, right? The assumption is if you don't touch the coastline, there's no way the water can be connected to you, right? Can't come in there. So that we say it's not hydrologically connected. So the way we'll do that is we'll need another layer. I'm going to bring in this town survey arc layer that was in our originally that we downloaded and unzipped. So I'm going to bring that in, and it's the same thing as the Boston boundary, but you can see it's got this dark black line, so that's what that is. So basically, I'm saying you've got to be touching that in order to count, right? In order to be connected some way to the coastline. So once I bring that in, now I can do another operation called a select by location. So under the map item up top in your up ribbon, you'll see in the middle select by location. So I'll click on that. And so the the items that I want to select by are this kind of the polygons, the flood polygons, and I'm going to choose intersect as a relationship, which just means touch. The lines, the municipal boundaries, make sure you're giving the lines one, not the polygons one, lines. And I'm going to say 1 meter because this will give it a little bit of leeway. So if it's not perfectly on touching, it's just nearby, it's close enough. That's what we'll say. And then lastly, so if I run it like now, what it's going to do is going to grab just the things that are touching the coastline, which is what we want to keep. But I know that what we're going to do is we're going to get rid of all the ones that don't touch the coastline. So in order to highlight the ones that don't touch the coastline, we're going to hit this little box here called invert spatial relationship. So it's going to basically, the default is to pick things that are touching, but then this will say, okay, do the opposite, get all the things that aren't touching. So anyways, we'll do that, we'll hit OK, and then it'll run the spatial selection, and then you'll see the polygons light up that don't have a direct connection to the coastline, right? So they're below the elevation that would be floodable, but they're not connected. So how would they flood, right? So now that we've highlighted the ones that don't touch, now we can get rid of them. So we're going to go back into our tools, and the tool that we're looking for this time is called, surprisingly enough, delete features. Okay, so this delete features is the one we want, and then we'll choose the polygon layer, that less than 286 one, and then it says it's prompting you. It says use selected records, which is the ones that are in blue, and that's exactly what we want, which is also why we made sure that we did the inverted one. So now we'll run that, and then you'll see it just threw out all these polygons in the interior that didn't have a connection. But interesting what kept there, right? So we can see this long stretch here, but all of that, even though it's far inland, has a direct connection, follows back to the water. So there's a possibility the water could travel all the way unimpeded if it were to get that height. So this constitutes our first layer for this one 2050 scenario, showing the minor flood water height that would occur under this scenario of 2.4 feet of sea level rise. And this particular water height would also mean that that area in pink has a 81% chance of flooding annually under that particular scenario. So these are areas that would be very likely to flood annually under that particular scenario. So what we're going to do next is we have 2 more layers to do, but it's exactly the identical process. It's just that you just use the next heights on our list. So those next heights we're going to be, instead of 2.86, we'll use 3.32 and then 3.62. So I'm going to, in the interest of time, I'm going to fast forward and just show that what that looks like at the end once we have those 3 layers together.